So here, this Newtonian design is, like I said, very popular. And you know it's a Newtonian design if it has, you look up the optical tube and it has a little hole up there, okay, to stick your eyepiece in. All of these, or most of them, require a secondary mirror. So this actually is what we call the primary mirror down here, okay, and this is a secondary mirror right here. So for the schools, remember I told you you kind of look out the butt of the telescope? Okay, so for the schools, this actually was the back of the telescope. Okay, that little annoying button thing, that actually was right there. That's your secondary mirror. Okay, which is before the focal point. Then it goes ahead and sends the light back to continue coming to a focal point right there. And remember, with telescopes, what you usually do is have a series of eyepieces handy. So we swap out eyepieces, and this is where the eyepiece goes. So that's my picture of an eye. You look in the butt. So the other two, this one is just they're kind of catch-alls. D, they're calling a coup de focus. Basically, can you see the primary mirror down here, and then you see at least a couple of secondary mirrors? Okay, but this one right here, B, I think I'm amazed. It actually is called a prime focus. So basically, as long as your telescope's big enough, you go ahead and have a little chair right there for somebody just to go sit there. I think that is so cool. Prime focus. Okay, so here we go. This is a reflecting telescope. You can kind of see the mirror back there. Now I mentioned that the ones that use mirrors, reflecting telescopes, they aren't limited by sagging glass. They're made of glass, but there's a coating over top of them. The thing is, you don't care about the quality of the glass. It can have bubbles. Basically, it can be supported, which prevents it from sagging. Okay, so there you go. A lot of times, reflecting telescopes are segmented too. We're going to see that here in a minute. But this is a Cassegrain design, so you look at the image back there. This is the primary mirror right here. It goes to a secondary mirror here, then back through the butt. Can you kind of see the segment lines on this one? Okay, this is a big telescope. There's like twin telescopes. There's a lot of telescopes in Hawaii. Okay. But you see the Keck Observatory. There's the domes right there. You can see the slit open. Kind of a pretty picture. All right. So kind of switching gears from telescopes that we might use to kind of other sort of telescopes. I mentioned that astrophysicists are great about basically taking every little tiny scrap of information coming from the cosmos and putting it into, does that make sense? So actually they use telescopes to gather radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, okay, all of those cousins. Now granted the telescope looks different and kind of works different a little bit, but it's gathering those energy photons. It's got the same idea going on. So kind of looking at both extremes, I want to give you just a glimpse at what radio astronomy might look like, and then also X-ray astronomy. So radio astronomy, if you remember, radio waves are so long. They are just so long. Okay, the wavelength is long, the frequency is low. So in order to make sense of this, basically you have to have a humongous, and we're going to see one on the next slide, a humongous, basically reflecting dish, okay, to take all of the information to a focal point. You either that, or you have a number of smaller telescopes that work together to send the same signal to create a common image, and that's called interferometry. So that's kind of the low energy, long wavelength. And then the other one we're going to take a look at is X-ray astronomy. So X-ray astronomy, you figure X-rays are right before gamma rays, so they're pretty darn energetic. Okay, so X-rays, you can't do the whole glass thing. You can't do the whole mirror thing because they just go through your mirror. So I have a picture coming up. Basically, they take kind of a glancing blow, and then they kind of reassemble an image to concentrate to make an X-ray image. Again, why would you care about X-rays coming from outer space? Well, sometimes some events are very energetic, and that image in the X-ray region of electromagnetic spectrum tells you a lot about that object. Then worse than X-rays would be gamma rays, okay? And I like this. Check this out. In order to create an image of like information in gamma rays, what they do is they find a gamma ray photon and they understand its trajectory, and then they basically backtrack where it was, and they create a picture that way. It's like, dude, you are so determined. Yeah, I just think that's neat, these different forms of astronomy, or astronomy looking at different energies. So this actually is looking at radio waves, okay? It's humongous. 305 meters is wider than 3 football fields, okay? And you can see actually the focal point, that thing hanging over the top, would be where the image is being concentrated because of the shape of the dish. So that's a radio wave telescope. And this is using interferometry to make an image in the radio wave part of the spectrum. So interferometry, it looks like an army of dishes, doesn't it? Okay. So what they do, and especially these over here, are on, like the caption says, they are actually on a train system, like a rail system. So you can locate them wherever you want to catch, to go ahead and get an image in radio waves. This up here is just star trails. Aren't those pretty? Just star trails. And then this is the X-rays. The one of the last topics I want to talk about is telescopes that actually orbit the Earth. Like, really? But yeah. So actually Chandra Observatory is a telescope that is orbiting the Earth. The Hubble Space Telescope orbits the Earth. Okay, and we'll talk about why you would want to do that. But so this is showing you how Chandra can take those energetic X-rays and go ahead and create an image of an object that's emitting X-rays. All right, so orbiting telescopes, gotta love them. This is the Hubble Space Telescope, affectionately known, the HST. It's got a big old long saga of it. It's done so many things in its life. I think it went up in, I want to say 06. Okay.
But it didn't do anything for a while.
Yeah, it didn't do anything. That's part of the saga. When it went up, okay, actually when it went up, its mirror, it is a reflecting telescope, the Hubble Space Telescope. Its mirror was just a little bit off. Like, dang it. How'd you like to be the dude who messed that up? But I heard the story behind that too, was the mirror was perfect, and then they took one last look at it, and they're like, no, it needs a little bit more off, and then they just messed up the mirror. So what they did then is to send up a space shuttle mission to basically insert a module to correct it for its incorrectness. So that's the Hubble Space Telescope. The thing about the Hubble Space Telescope also is I think it's had its last servicing mission, I'm not sure. They don't last forever, quite frankly. And resources and all that. It's being replaced by the James Webb Telescope. I don't know, but Hubble's been awesome. So why would you want to put Hubble Space Telescope in outer space? Well, it's becoming increasingly difficult to find dark skies anymore. So just hear those astronomers whine about it. And the problem with light pollution is that it has consequences on like wildlife, not just astronomers, but you know, it's a whole, and an energy thing, okay? But light pollution is an issue. And there are organizations out there that you can join to try to combat light pollution. But another reason that you want to go ahead and take your telescope and have it orbit the Earth instead of on Earth's surface is because the Earth's atmosphere is not steady. It's turbulent. So if you've ever heard the song, you know, Twinkle, Twinkle, Little Star, okay, stars twinkle and planets don't. If you've ever heard that old adage, there's something to that. But the reason stars twinkle, quite honestly, is because the light from that star is being kind of distorted by the Earth's atmosphere. Now, if the Earth's atmosphere were steady, okay, like the same temperature, the same composition, you'd get no twinkling. Sometimes, and I've heard like my friends at the observatory talk about this, sometimes the sky is a lot more turbulent than others, and you can a lot of times see it with your naked eye. If it's like a really twinkly star night, it's not a good night to try to find detail through a telescope, okay? A lot of times it's just chunks of air that are at different temperatures that cause the refraction that makes it dance. That's what twinkling is. So twinkling makes it hard to see detail. And remember we said detail is measured by angular resolution of the telescope. Let's see. So I've got kind of left and right sort of thing. So this is from the same set of stars. Okay, this left one is from a telescope on the Earth. Okay, and this right one is actually the same view from a telescope that's orbiting the Earth. So you definitely can see better angular resolution, more detail with the second one, the right one. The Earth's atmosphere isn't causing those distortions. Just a general statement, you know, you try to find a location that you don't have light pollution is not an issue. And it's dry, and upper elevations kind of gives you a fighting chance. You don't have as much as the Earth's atmosphere to give you turbulence. So we looked at, this is like one of the pair of the Keck Observatory, so what we looked at earlier. The thing about light pollution, I think if you've got some money sunk into something like this, I mean, you could get really picky about the urban areas that are kind of encroaching on your dark skies. So, all right, so the Earth's atmosphere not only gives us turbulence, twinkling, but the Earth's atmosphere, fortunate for us, actually can block out some types of energy. So actually from left to right, you see the different, the cousins, the different types of energy. So here we see the energetic gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and then radio waves. Okay, and then the way this figure works is the longer the arrow, let's kind of pick on visible, okay, the longer the arrow, the more that energy can get through Earth's atmosphere. Okay, the shorter the arrow, like up here, okay, then actually that means it blocks, at least to some extent, that energy. So we're good with visible and we're good with radio waves, but we've got some issues with the other types of energies. So then across the top, it actually said, see, we saw Chandra, right? Chandra, okay, the X-ray observatory. And then there's Swift and Fermi, Hubble Space Telescope looking in the visible region, Spitzer looking at infrared, and Planck infrared radio, or microwaves. I think Planck might be microwaves. Okay, so there you go. But you know, these are only NASA's, you know, NASA, HART, right? Okay. If you get to looking into what other nations are doing with regard to studying space, I think it's amazing, because if you ever see, and we might be seeing a little bit of this, if you ever see, instead of NASA, if you ever see ESA, that stands for European Space Agency, which is kind of analogous to our NASA. And actually there are joint ventures between different groups, which is kind of nice to see.
What's NASA funded by now, since the government doesn't do it anymore?
No, NASA is still funded by the government.
Is it?
Yeah.
They were talking about not doing it for a while, so I didn't know if they ever quit or not.
Yeah, I think one of the things that NASA has a big budget, and like certain line items are probably been hit hard. Like I think their outreach, their funds have been cut there.
Well, I know that like they don't have any interest in really sending anyone up as much anymore.
Yeah, and
I
some.
was just wondering.
Yeah, you're onto something, because I know, like in the news, they're talking about if you go to Mars, you know, it might even be a private venture, which I have mixed feelings about that. So.
They've got Orion on the line right now. They're getting ready to send people back up.
Yeah.
You know, well, 2020.
NASA is getting ready to send people up.
Coming around.
Well, that's when Orion's supposed to start doing its test flights in 2020.
And Orion, is that the Mars mission?
No, it'll eventually, they said it could
Right.
eventually go to Mars, but right now I think it's Moon.
Okay. So going back to the moon, NASA or Orion program in, yeah. So I don't know.
I think they should be. I don't think there's any reason to stop trying to explore out there.
I agree. It's more than just Tang that actually has come from the space program through over the years. You know, the beverage Tang, really, it did come from the program. But we've learned a lot in our exploring space this way. So I don't know. I agree. So one last thing. If you're confined to the Earth's surface, there is a way to try to combat twinkling. And it's called adaptive optics. And what this slide does is kind of walk you through adaptive optics. Remember, twinkling is turbulence in the Earth's atmosphere. It basically sends up a laser signal, and it looks for the turbulence, and then it basically corrects for the turbulence it sees. So when I think of adaptive optics, I think what's important, one among other things, is actually you need to be able to reshape your mirror. So again, we're talking segmented mirrors. So, but kind of from left to right, actually this image here on the right is the real deal. I believe this must have been taken in the infrared region of so it's not a visible image. But there are really two objects in this left one too. You just can't resolve two objects. If you're into looking at a type of object called binary stars, okay? Binary stars really need a nice, steady sky in order to see them. So that's what that kind of reminds me of. Okay, we're going to go on into the next chapter. Which is chapter 6. So we've got, 20 minutes or so to do chapter 6, see how far we get down the road. Now, for my night class, we actually had enough time that I actually showed like a full-length documentary, a Brian Cox documentary on this topic. So we'll see how far we get, and if I can kind of show you some of that video. It was really cool. So, anyway. So, this unit has 2 science chapters, okay? So we talked about motion, gravity, the whole chapter 4. And then chapter 5, we talked about light and ended up with telescopes. And then chapter 6, finally, we're kind of segueing again back into kind of celestial objects, looking at our solar system. But the whole thing of motion and light and telescopes, that's kind of important to chapter 6, chapter 7, chapter 8, okay? I think. So kind of a bird's eye view of our solar system, right? Among other things, we'll start to kind of get oriented. You can kind of see, we talked about the plane of the ecliptic earlier. Okay, so the plane of the ecliptic is what holds the orbit of Earth as it orbits the sun. And all of the planets basically orbit the sun on the plane of the ecliptic. The other thing is, I said that the Earth orbits the sun counterclockwise. If you're looking down at the North Pole, all of the other planets orbit the sun counterclockwise in the same direction. We have 4 inner rocky planets, so I'll go ahead here. So the sun's in the middle. These aren't drawn to scale. We have Mercury. What's after Mercury? Venus. And then we have Earth. And then we have Mars. Okay, exactly. And those are all, what the slide says, those are all rocky. Those are rocky inner planets. So if our goal is to say, how did our solar system get to be the way it is? Well, we need to base our theory on observations. Those are the observations. Those are the facts, ma'am. So then after Mars, we have an asteroid belt. But after that, we have Jupiter. And then Saturn. And then Uranus. and then Neptune. Okay, so these are the outer planets, and their surface is gas, so they're gaseous planets. Sometimes called the Jovians, and I introduce that here in a minute. Okay, so I have a slide on everything, just a kind of quick and dirty slide. We have a whole chapter on the sun, but just a quick and dirty look at the sun. The sun is in the center of our solar system, and actually we're going to see that what formed our solar system, which is the sun and the planets, and actually little crumbly things called asteroids and comets, it started out as one big common pot of stuff, okay, what we call a solar nebula. And of that solar nebula, our sun got like 99.8% of the solar nebula stuff, okay, so it was a hog. The sun is mostly made of hydrogen and helium, and the sun in its core is great has a nuclear fusion going on to convert matter to energy. A little bit of matter into a lot of energy. So then moving from the sun to the first planet, that would be Mercury. We are fostering kittens right now, and we've got a set of kittens called the planets, and Mercury is just crazy. Pluto is just the most adorable one. We're bottle feeding him. So anyway, there's Mercury. It's the closest planet. Mercury is like, you know, when you go to Walmart and you look at the chickens that are on the spigot thing, you know, like they're still cooking, they're roasting, the chickens are roasting, okay? Mercury reminds me of basically that turny thing got broken, okay? So picture that, and basically part of your chicken is charbroiled and the backside of your chicken is cold. So Mercury, basically the side of Mercury that's next to the sun is very hot, okay? Side of that's facing the sun, 425 degrees Celsius. The backside of Mercury from the sun, very cold. Okay, why? Because it rotates so dang slow. It has no atmosphere. Okay? So Mercury, it kind of looks like the moon. Okay? To me, it's got that kind of gray, sort of powdery, regolith sort of look into it. We'll talk about kind of, is it still geologically active and that sort of thing, which the answer is no. We'll talk about that actually beginning unit 3. So the next planet after Mercury is Venus. Okay, sometimes these are called the inner planets because they're inner from Earth's orbit, okay? So we have Mercury, Venus. Now the thing about Venus is that it's shrouded in mystery. No, really. Venus has a pretty thick atmosphere, and the major component in Venus's atmosphere is carbon dioxide. And you know what we think or know about carbon dioxide that we're increasing in the Earth's atmosphere. Carbon dioxide is great at being like a blanket. So it's kind of a runaway greenhouse effect. So it's very hot on Venus, 470 degrees Celsius, daytime, nighttime. And kind of the reason basically the nighttime is still so darn hot is because the blanket, okay? If on Earth, if we have a cloudy evening, okay, our evenings can stay pretty darn warm, which could be good or bad. Okay, clouds actually kind of act like a similar thing with a blanket. Okay. So the thing about Venus, too, is that we haven't, but the Russians actually landed a probe on Venus, which transmitted for a little bit until the aliens came and smashed it. No, I'm just kidding. Okay. But Venus actually, its surface is, we'll see a picture of its surface when we study Venus. But we really can't see the surface of Venus very good, but what we do is basically they have had orbiters basically send down radar through the thick clouds and look for the echo and make a topographic map. So we kind of have a sense for what its surface features look like. Okay. Those clouds, you know, it's mostly carbon dioxide, but the clouds are sulfuric acid. Really? Yep. So anyway, that's Venus. Road trip. The Earth. So we'll talk about where Earth's water came from actually in this chapter, but one of the things about the Earth and water is it's the only planet that actually has liquid water on the Earth's surface. Now, when we get to talk about some of the moons around some of the gas giants, we're going to see that actually we believe there's liquid water underneath kind of a crust of solid water. Isn't that crazy? Not the gaseous planets, but the moons orbiting the gaseous planets. Anyway, so we have liquid water, we have life. As far as we know, we're the only planet that has life. But if you're one of these that keep, guessing or hoping that they're going to find like life on Mars or microbial life, not the alien sort of life.
Right now in Sol, this is the best chance, right?
Right. It's a good one. So then the last terrestrial or rocky planet is Mars. Now Mars is like a hot spot of activity. Oh my gosh. I think it looks like this is maybe the latest. Let's see. Curiosity. Yeah, Curiosity. There are several rovers on the planet Mars just from us. And I know Curiosity is sending back pictures. I kind of feel like with regard to cool stuff to do with space and planets, I feel like that the United States is kind of desensitized. I mean, they'll send back awesome, amazing things, and we're like, yeah, I know, I've seen Mars. Really? Have you seen Mars? Okay. But anyway, so opportunity, lots of stuff going on. There are actually definitely orbiters looking for different things also around the planet. Mars, even at as the crow flies, even in this picture, can you see this crazy rift right there? Okay. So that is like a big, it's like the Grand Canyon, but even deeper, I think. And it stretches like to cover the United States from our west coast to our east coast. That's how big that is. It's a canyon. And it's thought that to form as Mars cooled. So it's called Valles Marineris. All right. So, yeah, there's Mars. And then we hit our gaseous planets, starting with Jupiter. Some of these, especially with these planets here, are artists' photographs that have been put together based upon information we know about the planet. So, for instance, this is actually taken from, remember Galileo saw moons around Jupiter? And actually that was a really important thing. This is one of the Galilean moons. This is like Io. Io is like a popped yellow looking thing. So like from Io, the moon Io, what would it look to look towards Jupiter, the planet it's orbiting? So Jupiter is the biggest of the gas giants, the Jovian planets. Jupiter has moons, okay, lots of moons, okay. And Jupiter, actually, we think of Saturn when we think of rings, but all of the gas giants have rings. So Jupiter also has rings. But you can kind of see the band feature. That is very pretty. So Saturn, here's Saturn with the rings. Okay, and I say rings because you can actually, what looks like one big ring is actually kind of like a series of rings. And as you might imagine, if we were to look close up at Saturn's rings, actually these are all little particles. Okay? One of the cool things, and see this is not an artist drawing. This is a photograph from the Cassini spacecraft that has been studying Saturn and its moons for a while now. But do you see this shadow back here? Is this not cool or what? Okay, that shadow is created because basically the sun is over here, okay, and the planet is casting a shadow on the rings. Is that cool? I just think that is so pretty. So just like Galileo saw moons orbiting Jupiter, if we look through a telescope at Saturn, a lot of times we can see some of its moons that also orbit Saturn. A big moon that orbits Saturn of interest is Titan, and that inset actually is kind of that greenish sort of creepy looking haze. That's around the planet Titan. And we have landed a spacecraft on Titan. And at least one. Okay, so the Jupiter and Saturn are kind of similar. They look similar, kind of orangish. And then we have Uranus and Neptune that kind of have this blue hue to them, kind of a blue color to them. And actually the blue, they are blue because of the presence of methane. I remember in this class when we talked about atoms and molecules, okay, or atoms and compounds. Okay, so in a methane, this is called methane. Okay, so in a methane molecule, we have a carbon and 4 hydrogens that are scooting off of it. I just think that is so cool that molecules or compounds can form like that. Okay, so one of the things, and I'll mention it now because it's a player, but this is an artist's rendition of Uranus. But can you see where Uranus looks like? It looks like its kind of rings is, and if that's the equator around the rings, it looks like its axis of rotation is tilted, and it totally is. Okay, so one of the things about the Earth is we said the Earth's axis of rotation is tilted 23.5 degrees, okay, as it orbits the sun. Okay, actually then, this planet, Uranus, its axis of rotation is tilted about 90 degrees. So if that is Polaris or whatever, basically, and the sun is here, as Uranus orbits, okay, the sun, it basically does this sort of thing, you know, spins on its axis of rotation. So if you're like me, you're like, dude, if the sun's there, this hemisphere is really cold, right? This part of the year. Yep, and you're right. Over here, okay, this hemisphere, now the same hemisphere is really warm. It's true. Its axis of rotation basically lies in the plane of the ecliptic. Okay. The next blue one, Uranus, Neptune. So again, Neptune has, you can see the rings around Neptune. Okay. There's actually kind of a banding feature, just like Jupiter has on all of the planets, gaseous planets. And it definitely has rings. This is one of my pet peeves. Remember I said the planet, not the planet, I said the moon Titan, that kind of creepy greenish looking thing that orbits Saturn. Okay, Titan is a really cool little moon. Well, there's Triton is also a cool little moon, but it is down around a different planet. So the moon Triton orbits Neptune, the moon Titan orbits Saturn. I hate those sort of things, you know? They're just like I hate reflector and refractor even, you know? Titan and Triton. Okay. So, yes. I think we talked about the whole Pluto being recategorized, no longer a planet, and we're going to talk about that just briefly here. So Pluto, of course, if you're jogging from the sun outward, you would, after you pass Neptune's orbit, you're going to run into Pluto's orbit, right? So Pluto in 1930 was discovered, and in 2006, it was downgraded from a planet to a dwarf planet, which is really cool. I think dwarf planets really rock, so just, okay. And the reason it was demoted, I think we talked about this, the reason it was downgraded was actually they found an object, and I have it here on a slide coming up, another object that was farther out from Pluto called Eris. Okay, so if you look at Pluto, it's definitely outside of the whole gaseous planet thing. So we have the 4 rocky planets, then we have the 4 gaseous planets. Pluto is more similar to a rocky planet, but honestly, Pluto is more similar to, because of it's got icy rocky, it's more similar to a comet, basically. And as I kind of go like that, that's where the comets are, okay? Kind of we have a couple sets of pictures of Pluto here. This on the left was the Hubble Space Telescope, which totally rocks. But this is what we knew of Pluto before actually this summer the spacecraft called New Horizons flew by Pluto. So exciting. Okay. So, and there are even updated pictures of this too, but this is Pluto now. This is Pluto. And it's got a heart. Can you see the heart in Pluto? I put that on my Facebook. I so did. So, it is so cool. So New Horizons. It was a big, hairy deal. My husband and I got like champagne and everything. You know, geeks that we are. So, I don't know. The thing about it is all missions are different. And this mission, the parameters of this mission, basically it didn't have the energy or the physics or whatever to insert itself in orbit. So basically, and it's got to be a scary thing to be one of those NASA engineers, okay? So basically, they flew it. They knew it was coming. They had to take a bunch of pictures, okay? Basically, they just had to go right on past Pluto. And so now this thing New Horizons is going out into outer space. Just like kind of, if you've heard of the Viking missions, Viking 1 and Viking 2. We've got a lot of those missions going out. There are websites to see where they are now. But New Horizons, so they took picture, just when they came up on it, right? And then it went on its way. I think there were like 2 qualities of pictures they took. There were like the kind of quick and dirty, get them back so we can all get excited. And actually, we still have pictures coming from New Horizons, the higher quality pictures that they took as they passed. So if you see New Horizons and Pluto in the news, it's the delay in getting those high quality pictures to us. So it's so cool, oh my gosh. So here actually Pluto has 5 moons, and you might say, hey, it has moons. You know that it's a planet. I'm like, no, it's not a planet. Okay. It has 5 moons. The biggest of the moons is Charon. So here's a picture of Charon that New Horizons took. The thing about Charon, the moon, and Pluto is Charon is so big, kind of relative to being a moon, that they actually orbit what we call a common center of mass. So the moon Charon doesn't orbit Pluto. Basically, Pluto and Charon do this little dance around a common center of mass, okay, because of how large it is. So just to kind of remind you how this works, okay, in 2006, why was Pluto changed its status? Obviously demoted. From being a planet to being a dwarf planet, okay. It met the first 2 criteria, okay, so because Pluto does orbit the sun, okay, and Pluto is spherical. The whole spherical thing comes with mass. It has a certain amount of mass. Over time, it's basically going to go ahead and it's going to shape into a sphere. But if you look at Pluto's orbit, it's got all sorts of stuff left from, we're going to be talking more about this on Wednesday, from kind of the beginnings of our solar system. It's got crumblies, comets, okay, other material in its, so it has not cleared its path as it orbits the sun, has debris in it. Okay, well, very good. This is a great figure. We're going to start with this on Wednesday.